In the last problem, you were probably wondering, why are we worried about the moment of inertia of a propeller, right? I mean, why do I really care? Well, when you get into performance aircraft that you're working on yourself, if you ever do that, or you've got some marginal plane you're worried about, some marginal engine you're worried about, it's really important because the moment of inertia, remember, the torque you have to apply to get a certain acceleration is tau. The torque is the moment of inertia times the angular acceleration. And so if you have an engine that can only provide so much torque, the moment of inertia of your prop is going to dictate a lot about what happens with that prop. And you don't want to overstress the gearbox or the engine or anything like that by having a prop out there that's just has way too much of a moment of inertia, right? And so you don't want to mismatch in your equipment, basically. And that's one of the reasons we look at this. So here we are. We're doing a calculation on how long does it take the prop to get up and spinning, right? And we're ignoring air resistance. Air resistance in this one is a graduate school problem. All kinds of cool things going on with that. It actually, by the time you get it up and spinning, if you're sitting still, there's a lot of cavitation going on. And so it's almost like it's spinning in this little vacuum when you're just kind of sitting there. All right, so how long in seconds will it take the prop to get going? We've got the moment of inertia. All right, we've got I. I is 6,100 centimeters squared. We know that we want to reach a final velocity of 2,100 RPM, right? And we know that the gearbox can provide a torque of 32 Newton meters. Well, we got units all over the place here, right? And just so you know, 30 foot-pounds is about 40 Newton meters to kind of give you a scale to the old English units that most people are more familiar with. How do we do all these conversions? Well, rotations per minute. So a rotation, we got a rotation per minute. I'm going to rewrite that real quick as exactly that, a rotation per minute. Well, a rotation is just 2 pi radians per rotation. That's easy. We've done that again and again. And a minute is 60 seconds. So we're going to multiply by 2 pi. We're going to divide by 60, and that's going to get us to radians per second, which is what we need here. Okay, we need to get from kilogram centimeter squared to kilogram meter squared. And all we really have to do is we got to convert centimeter squared to meter squared. Here's how I think about conversions like this when they are when you've got a power of some sort of exponent. Well, we've got a centimeter squared. What's a centimeter? A centimeter is 0.01 meters squared. All right. 1 centimeter is 0.01 meters. How do I get there? Well, 100 centimeters is 1 meter. That means 1 centimeter is 1 over 100 meters, which gets us to 0.01 meters. All right. 0.01 squared, well, that's going to give me 0.0001 meters squared. So all I have to do is multiply my 61,000 kilograms centimeter squared by 0.0001 meters squared per centimeter squared, and I get this converted without any problem. All right, so now I have my moment of inertia. All right, I have my moment of inertia. I have omega. I have tau. Well, because I have tau, we know, I've said again and again, tau is I alpha. I can find alpha. All right, so I know alpha. Alpha is the torque over the moment of inertia. So I've got the angular acceleration. I've got the velocity we're headed to. We start off at rest. So omega is alpha t plus omega naught, but omega naught is 0, right? Omega naught is 0, so omega equals alpha t. We know omega, we know alpha, we can find t. And that's how you solve problem 8.